Section 7.2 is called active power. We're going to look at three different circuits in this chapter, and they're going to help us really get a good understanding of what active power, reactive power, and apparent power are. So let's work through these. Let's get something to look at here. Put some sinusoidal waveforms of voltage and current, and look at the power waveforms that we plot from that. And remember, we're using the same concept that we were using in the instantaneous power section, the one before this. And you know what we're doing is we're multiplying the values of the instantaneous voltage times the instantaneous current, and we're looking at those with different situations. The first with a resistor, the second with an inductor, the third with a capacitor, and walking through these to see and get a good feel for what the difference is between them. Our first circuit is in reference to active power. Now, to begin with, there's a little asterisk beside the active power term. And remember, when we're talking about active power, some people call that real power or true power. You know, but what we're talking about here, and the term that he uses to reference in our textbook is active. All right. And, you know, also, you know, we might even think about this in terms of RMS values. So what we're looking at here in this figure 7.2a, here we have a source of an AC voltage. And then, you know, this is what that voltage is. Why would you have a difference between those two voltages? Well, maybe there's some sort of internal drop, you know, within the generators. But anyway, what the load sees, and of course, here's the load, is this voltage E. This source is supplying a current I to the load. The polarities are given just for reference so that we can have something to work off of, you know, from plus to minus. And we see that current is flowing into the positive terminal of the load. It's purely resistive. So, you know, that is what we're looking at. And then these are effective values. And as we walk through this thing, we can see, because this is a purely resistive load, that the voltage and the current are in phase, which makes sense. Purely resistive, current and voltage are in phase. Another look at this, if we were to place a watt meter into this circuit, say we put the watt meter, and if we are measuring watts, we have to connect across the source and have all the current flow through it. And what that would look like would be this representation here. Here's our watt meter, and we see that the power is flowing to the load. All right, so that's what we have up to this point. And then finally, to get a better picture of what's going on in this, we're going to look at the final curve here. And what we're seeing is a plot of, let's see if I can figure this out here. Here's the voltage here. And then let's change the color to yellow, and the current here. Now, taking instantaneous values, I'm able to plot the power curves, and those are indicated here. All right. And just like we mentioned earlier, the power frequency, the power curve frequency is always going to be 2 times whatever the voltage and current frequencies are. So we're seeing, like, from here, there's one full cycle of voltage and current, and within the full cycle, we have 2 cycles of power. So the power frequency is always twice, and we're going to come back to that and you know, reference that. Again, just so that we know this, you know, if in terms of, you know, the effective values of things, when we're thinking about, you know, that conversion, then we need to remember to calculate the peak values. The peak values are always going to be the square root of 2 times the effective value, be it current or voltage. Basic fundamental thing there. And when we're thinking about that, these are effective values across there. And then by multiplying the instantaneous values, we get the instantaneous power, and that would be in terms of watts. Okay? Now, the power wave is, as we look at this, let me clean this up a little bit. Let's clean this up some. The power wave, maybe blow it up a little bit for us too. The power wave, it says, consists of a series of positive pulses that vary from 0 to a maximum value of, what would it be? Well, it would be the square root of 2 times the effective value times the square root of 2 times the effective value of the current. And what would that be? Square root of 2 times the square root of 2 would give us 2 times E times I. Or another way to phrase that would be 2P, because that E times I is just equal to P across there. And that would give us the maximum value for that. The fact that the power is always positive, nothing below here, below the 0 point, the fact that the power is always positive reveals that it always flows from the generator to the resistor. And this is one of the basic properties of what is called active power. This is what we've always dealt with up to this point. Active power, true power, effective power. Okay, it never changes direction in terms of, going below 0. And the direction of the power is always to the load, as shown. The average power is clearly midway between, 2P, and that is given to us here. Okay, so the average power is between 2P and 0, so its power is 2EI divided by 2, which would just be E times I, and that would be in watts. And that would be indicated on that watt meter. The two conductors that are leading to the resistor in 72A here, all right, this is leading to something new for us too, and a good new way to think on some of this stuff. But he says those two conductors leading to the resistor, they carry active power. And unlike in circuit analysis where we track current flow through components, what we want to think about here is that power doesn't flow down one conductor and return to the other, right? Power doesn't work that way. When we're thinking about power, power flows over both conductors. And consequently, as far as power is concerned, we could replace both the conductors by just a single line. And we do that with what we call our power flow representation. It's not that tracing current through components anymore. It's just this idea that power flows, and it flows through both conductors. And in general, when we're doing this, the line represents any transmission line connecting to devices. Doesn't matter how many conductors you actually have. And then finally, the last thing in this, when we look at this set of conditions, and this is important too, but we want to think of the generator. The generator here is an active source, meaning it is supplying power to the load. And the resistor is an active load because it is receiving active power. The symbol for active power is watts, or W for watts. We've always known that. Sometimes, of course, we'll have kilowatts, or when we get into larger systems, we even think about megawatts.